So in the previous video, we were introduced to the idea of a colligative property, which is a property that depends on the concentration of the solute particles, but does not depend on what those particles are. So they can be molecules from things like glucose, or they could be ions from things like sodium chloride, like sodium and chloride ions. And colligative properties do not depend on what those particles are, but rather the concentration of those particles. And we talked specifically, while it's not the only colligative property, we talked about osmosis. And so now we're going to look at red blood cells and think about those in relationship to osmosis. So when you have two solutions with the same osmotic pressure, so another way to say that would be the same particle concentration. The word to describe that is isotonic, right there. So they have the same osmotic pressure, which is related to the particle concentration. Remember, a higher concentration is equal to a higher osmotic pressure. Okay, so these would be two solutions that when we looked at their particle concentration, they would be the same. And when you have this solution, the water is going to flow at equally back and forth across the membrane. So it won't be moving more in one direction than another. It will be flowing equally. Now for our reference, we have solutions of known concentrations that would be considered isotonic with a red blood cell. And here are these solutions. Now, you do not need to memorize these solutions. We'll refer back to them. But so just so we have a reference, we have these solutions that we know are isotonic with the body. And we're talking about red blood cells. Okay, so the concentration of these solutions of their particles is equal to the particle concentration in a red blood cell. Okay, so just keep that in mind. And here's the image here from your textbook. And notice it has blue arrows of the water going in and out of this nice illustrated red blood cell. The red blood cell is very happy. Water's going just equally in and out of it. So let's talk about a situation when the red blood cell is in a solution that is not isotonic with it, or another way of saying does not have the same particle concentration. So our first example is going to be a solution that is hypotonic. Right here, hypotonic. So the word hypo means lower. Like if you are, hypoglycemic, or it means you have low blood sugar, right? So hypo means going to be lower. So this is lower. Okay, so you see there, a hypotonic solution has lower osmotic pressure than body fluids. So another way to think about that, it's related, the solution has lower particle concentration. Now what we need to remember is it goes from low particle concentration, the water, will flow toward the side that has higher osmotic pressure, or higher particle concentration, either one. And the red blood cell itself is surrounded by a membrane. Okay, so we're flowing across that. Remember, it goes low to high. So if the solution is low and lower than the red blood cell, then you can see with their blue arrow, I'll draw it more boldly right there, the solution is going to flow more readily into that red blood cell. Now, if you look at the previous slide, the red blood cell's a little flat, but now it looks like it's puffed up. And so here, let's read through the first bullet point. The concentration of the particles outside is lower than what's inside the cell. So it's going to go from the water will go from low particle concentration to high particle concentration. And so the water will flow into the cell. Eventually, the cell could burst because it can't contain that as the water keeps flowing in. The bursting of and rupturing of red blood cells is called, you can see down here, the word is hemolysis. Now, there could be a medical reason that they would want to put in a hypotonic solution. I don't know, I'm just imagining maybe somehow it's dehydrated. Maybe the cells need extra fluid or something, and so if they put in an hypotonic, it might increase the flow into the cells. So it's not like it's always bad, it's just, but if it's not controlled, this is what would happen. Okay, so that's hypotonic. And then the next one is hypertonic. And so this little prefix hyper, so hypo means low, hyper means high. Like if you have hypertension, you have high blood pressure. So this is a solution where the solution has a higher osmotic pressure or a higher particle concentration than what's in the cell. And again, we have to remember it flows from the low side of the membrane to the high side of the membrane. And so in this situation, and you can see the line that they drew, and I'll draw over it, it's going to go from inside the cell out. So what happens to the cell then is the fluids are pushed out of it, and so then the red blood cell starts to shrink. And so if we look at the bullet points, it says the concentration of particles outside is higher than what's inside the cell. So the water's going to flow from the low to the high particle concentration. So it will go inside the cell to outside of the cell. The cell will start to shrink. The process of this shrinking is called crenation. And I do not know a lot of medical things, but I do remember once them talking about I think it was the drug mannitol. Now, if I'm wrong, I'm sorry. But being used for brain swelling, and it's a hypertonic solution. And so by using that, if the cells in the brain were swollen, it would cause those cells to shrink. The liquid would come out of this. Another example, which is not about cells, but about like when you make pickles from cucumbers. So it's a similar idea. You have your cucumber and you put all sorts of spices and stuff in, because remember the water flows both ways. So if you put things in the water that would add a flavor, it will go in the cucumber and as the liquid comes out. But you put it in a brine, which is a really, really highly concentrated salt. So you put that cucumber in a solution that is hypertonic to the cucumber. And so the water is pulled out of the cucumber and into the solution. And so then you get that shriveling or shrinking of the cucumber to make it a pickle. So you can kind of see that working, and it also happens with cells. So now we're going to do an example where they give us solutions and ask us if it's hypertonic or isotonic or hypotonic with the cell. So it says, what happens to the red blood cell when it's placed in each of the following solutions? Now to do this, we're going to need to refer to our isotonic chart. So let's, the first slide. But let's look at letter A, and I see that it's a glucose solution, 3%. So I'm going to go back, and I want to compare it to the glucose solution. It's easiest when we can compare and they have the same chemicals, because then we don't have to worry about calculating the particles. So so the red blood cell is the same as a 5% glucose. Okay, I'm going to write that below so I don't have to keep. So the red blood cell is, I'll just put RBC, is 5%. So remember, I want us to remember it's going to go from low to high. So our red blood cell, this is our solution. So our solution, the solution is lower. So it's going to flow from the solution, low to high, into the red blood cell. So we have placed it in a hypotonic solution, right? Because the solution is 3% and our reference red blood cell is 5%. And in hypotonic solutions, the water will flow into the red blood cell. So what is going to happen is this is going to swell the cell, and eventually it could result in hemolysis. Where's my Y? Okay, let me look back. I don't know why it's all of a sudden not. Oh, Lysis. I don't know, guys. Hemolysis. Okay, so hypotonic solution because 3% is less than the red blood cell, which is its reference is 5%. All right, so that would be letter A. Then letter B, I have KCl solution. Okay, so I'm going to go back and look. KCl is an ionic compound. So let's go back and look what we have to work with. And you don't have to memorize these. So they don't give me KCl. And I didn't look. Was it molarity? Sorry. Yeah, it's molarity. Letter B is molarity. Okay. So I'm going to use the 0.15 NaCl. Because they don't give me it's ionic and so is KCl and it's in molarity. You got to use the same units. So that's our reference. All right, so I have the red blood cell is 0.15 m NaCl. So they're not the same, so I'm going to calculate it. My solution is 0.15 molar KCl. KCl has 2 particles. So times 2, so that would be 0.30. And my red blood cell, its reference would be 0.15 molar NaCl. NaCl also has 2 particles, sodium and chlorine. So both of them have the same particle concentration. So letter B, this would be isotonic. And so the cells, it would flow freely, so it would flow equally. So the cell would just remain the same in that solution. Okay, so now let's look at letter C. So again, so I have molarity, and then I have sodium carbonate, which is isotonic. So I have to use the same reference because I need something with molarity. But they're not the same chemical. So let's see, I have 0.15 m. Okay, sodium carbonate. It has 2 sodium. How do I know? Because there's a 2 there. And carbonate is a polyatomic ion. So it has 3 particles. And so this is times 3, so that's 0.45 m for the, this is the sodium carbonate, that's our solution. And we know from the red blood cell from our previous one that this is 0.3 m. So in this example, the 0.45, so this solution is going to be higher compared to the red blood cell, which is low. So we know it goes from low to high. So we're placing it in a higher solution. So that is hypertonic. And so when it's the cell's going to shrink, it's going to go out of the shell. And this is called crenation. So you may need to go back. There's a couple things I could think you could review, like you might have to think about ions again. You might have to look and just remind yourself about hypotonic, hypertonic, and do that kind of thing. But just kind of concentrate on each little piece. And if you have any questions, feel free to let me know.